Okay, taking a look at section 14.5, we are now going to be talking about directional derivatives and the gradient. So we talked about partial derivatives, and partial derivatives told us, okay, when you go along the function in the direction of the x-axis, what is happening to your function as a result? Or when you go along the function along the y-axis, what is happening to your function as a result? Directional derivatives say, okay, well, what if I don't just want to run along the x-axis or the y-axis? So kind of going back to that dome example, if you have some dome, I'm going to be drawing a lot of domes, by the way, especially when we get into maxes and mins. What this is saying is, all right, well, what if I don't just want to travel along the x-axis or the y-axis? What if I want to travel in the direction of some random vector? What if I want to know what happens to my function as I travel up the function this way right here in the direction of this vector? That's what a directional derivative does. It says, hey, we're not just limited to traveling along the x-axis and y-axis. We could travel along any direction vector and see what's happening to our function as a result. Okay? So in order to talk about how to compute a directional derivative, we need to talk about what the gradient is. The gradient is this thing right here. It's denoted by this little upside down triangle. It's not a delta. Some people call it del, but I find that really confusing. I just refer to it as gradient. So the gradient of f is basically a vector represented by the partial derivative of f with respect to x and the partial derivative of f with respect to y as the two components of that vector. If you're in 3D, then your gradient would be the partial with respect to x, with respect to y, and with respect to z. Pretty easy to compute computationally. We also need to understand what a gradient is. And what the gradient does is it tells you, looking at your looking at your surface, your mountain range, it tells you at a certain point, what direction would you travel in if you wanted to go the direction of the steepest ascent? Obviously, I don't know why you would want to do that, but if you were on a mountain range and you're at some certain point and you wanted to know what the steepest direction you could possibly travel in from that point is, you would calculate your gradient of that function. Okay, so the gradient tells you the direction that you would put your tangent line in order to get a maximum slope or a steepest ascent. That's what a gradient is. Now we can use our gradient to help us find what's called a directional derivative. And to compute your directional derivative in the direction of any unit vector, what you're going to do is you're going to take a dot product of your gradient dotted with the unit vector in the direction that you want to travel in. Okay, I like to remember this as an acronym, GUD. G meaning you compute your gradient, U meaning you compute your unit vector, D, dot them. Okay. So the other thing that we want to point out here is that you can also be asked a question on maximizing your directional derivative. So if they ask you what direction you need to travel in to get a maximum slope or a steepest ascent, that's your gradient. If they want to know what that maximum slope or what that steepest ascent actually is, then you take the length of your gradient to get that. Okay, so that's what we're saying here. We're going to do examples. We're going to make some sense out of that. Something that's also worth noting, even though it's fairly obvious if you take 2 seconds to think about it, if this gives you the quantity that represents your maximum ascent, so your steepest slope up, if you want to know your slope is descent, your steepest slope down, you would just negate that quantity, because obviously whatever your slope is, wherever you have the steepest slope, that same point is going to be where you have the steepest descent as well, except it would be negative if you're going down and positive if you're going up. So that's what we're saying there. Let's do some examples. All right, so this one here says, consider this function. Part A says, at the point 1, 2, find the rate of change of f of xy in the direction of this vector right here. All right, so these should be keywords that immediately clue you in that we're dealing with a directional derivative. Find the rate of change derivative of this function in the direction of a certain vector. Rate of change in a direction of a vector is a directional derivative. So I'm going to kind of go through my 3-step process here. My first step is I want to find the gradient. And remember, my gradient is denoted by this upside down triangle of f. And I'm going to compute each component of that gradient kind of down below, and then I'll go in and fill in what they are. So the first thing I'm going to do is I'm going to take my partial derivative with respect to x. If I take my partial derivative with respect to x, that's going to give me 6x minus, in that square root of 1 plus y cubed, that is all just a number hanging out in front of x. So we're just going to get root 1 plus y cubed. And then if you take the partial derivative with respect to y, that's going to go away. And then we're going to get minus x. The derivative of square root of 1 plus y cubed is going to be 1 over 2 times the square root of 1 plus y cubed. And then chain rule says times the derivative of 1 plus y cubed, which would be times 3y squared. Okay, what we specifically want to know is we want to know the gradient at a given point. We want to know it at 1, 2. So what I'm going to do is I'm going to evaluate my gradient, each of my partial derivatives, at 1, 2. So if I plug in a 1 for x and a 2 for y, 2 cubed is 8, 8 plus 1 is 9, so that'll give me 6 minus 3, which is 3. And then if I plug in a 1, 2 into my fy, that's going to give me negative. Plugging in a 1 for x, that'll stay 1. That'll be 3. 2 squared is 4 over 2 times 3. So the 3's will cross out. Negative 4 over 2 is negative 2. So overall, my gradient is 3, negative 2. And that's kind of my step 1 of this process. Step 1, find the gradient. Step 2, find the unit vector. So if we want to find the unit vector in the direction that we're traveling, we're going in the direction of this vector right here. So if I want to find the unit vector in that direction, I'm going to take that vector and divide it by its length. So I'm going to take the vector 2, negative 1 and divide by its length. So that would give me square root of 2 squared, which is 4, plus negative 1 squared, which is 1. So I'm going to write that as 2 over root 5, comma, negative 1 over root 5. So that's step 2 of my process. And then step 3, to find our directional derivative. And by the way, the notation on this is pretty awful. Directional derivative would be d sub e of our function f at the point 1, 2. So d standing for directional derivative in the direction of this unit vector of our function at this point. So that's our directional derivative. What we're going to do is we're going to take the dot product. So gradient, unit vector, dot them. So if we want to take our dot product here, we're going to take our gradient, 3, negative 2, and we're going to dot it with our unit vector in the direction that we are traveling. And when we do that dot product, that'll give us 6 over root 5 plus 2 over root 5. So overall, this will give us 8 over root 5. That would be our answer to part A. Part B says, and these are kind of just finisher questions. A lot of this, we've done the grunt of the work in part A. The rest of this is just kind of like, okay, can you interpret that a little bit? So part B says, at the point 1, 2, in which direction is this function increasing the most rapidly? So if we're looking for a direction with the most rapid increase, what we're looking for is our gradient. Okay? So our gradient, we've already calculated as 3, negative 2. So there's nothing left to do. This is either you know it or you don't. The next question says, at this point, what is the maximum rate of change? So this is the direction that we would need to travel in order to obtain the maximum rate of change. If we want to know what the maximum rate of change is, then what we're going to do is we're going to take the length of our gradient at that point. So we're going to take the length of this vector here, which is 3 squared, which is 9, negative 2 squared, which is 4, So this is the direction of our maximum rate of change. This is what the maximum rate of change actually is. And then part D says, in which directions is our function not changing at the point 1, 2? Okay, so let's go back to what a directional derivative actually is. A directional derivative at a certain point tells us how much our function is changing at that point. And we computed our directional derivative by taking our gradient and dotting it with the unit vector in the direction that we need to travel. And what they're saying is, in what direction, so in other words, what is the value of this unit vector such that our directional derivative is not changing? In other words, our directional derivative is 0. So we want the dot product of our gradient and our unit vector to be 0. We already know what our gradient is, 3, -2. What we're solving for is, what is this unit vector going to be? And you can call it whatever you want. You can call it xy, you can call it ab, doesn't matter. Essentially what we're doing, if you go back to part A, is we're saying what direction do we need to travel in order for this to be 0. So we already know our gradient. They're giving us what we want our directional derivative to be, and we're going back and solving for what direction do we need to travel in order to obtain that result. That's the idea here. Now, if you compute this dot product, you're going to get 3x minus 2y equals 0. And you'll notice here what happens. We have two variables, but only one equation. It's not technically solvable. However, the idea is that there are a lot of answers that can solve this, and as long as you choose one, that'll work. Let me explain what I mean. You can choose any value of x and y that'll solve this. And you can even go a little bit further and solve for y itself if you wanted. You can say, okay, well, 2y equals 3x. So anytime y is equal to 3/2 x, that'll satisfy this right here. So let's just say, for example, that I'm going to let x equal 2 and y equal, if x is 2, then y has to be 3 as a result. So one direction that we can travel in is the direction 2, 3. And that would make our directional derivative equal to 0, which would mean that our function is not changing at this point. However, it says to give the direction as a unit vector, and this is why it doesn't matter what we choose, as long as y is always equal to 3/2 x. You can choose any value of x. It'll give you a corresponding value of y, and no matter what you chose, when you scale it down to a unit vector, it's all going to be represented by the same direction. So the unit vector in response to 2, 3 would be 2, 3 divided by its length, which would be 4 plus 9. So this would give us 2 over root 13, 3 over root 13. And not just 2 over root 13 or 3 over root 13, but plus or minus. Because if you get 0, it doesn't matter if you get 0 or -0. 0 is 0. So technically you can go and when these are positive or when they're negative. And if you wanted to, I'm not going to waste your time doing it, but if you wanted to, you could choose other values for x and y. So let's say you chose x to be, let's make it something that works out nice, 4. And if x is 4, then y would have to be 6 as a result. If you were to take the unit vector of the vector 4, 6, and if you were to actually simplify this down, you would end up getting the exact same thing. So that's what I mean by it doesn't matter whether you choose 2, 3 or 4, 6 or any values that solve this equation right here. When you scale it down to a unit vector, it'll all be the same. All right, we're going to take a look at another example. The one we just did was in 2 dimensions. We only had a function in terms of x and y. Well, actually, it was in 3 dimensions, right? We had some function of x and y, so that's going to give us a height. In any case, we only had 2 variables. Here, I'm going to do something where we have 3 variables. And I just want to show you how this can be worded a little bit differently. I don't want it to mess with you if they word things differently on the exam. All right, so given some function here, this says at the point 0, 1, 2, find the maximum rate of change and the direction of the maximum rate of change. So the direction of the maximum rate of change is our gradient, and the actual maximum rate of change would be the length of our gradient. So that's all this is asking us to do. Let's go ahead and do it. So to find our gradient, the first thing we need to do is compute some partial derivatives. So if we take the partial derivative with respect to x, that first term will drop out. And then here, if we have e to the xyz, yz will come down in front, and then that'll leave us with e to the xyz. If we take the partial derivative with respect to y, that'll give us z plus xz e to the xyz. And then if we take the partial derivative with respect to z, that will give us y plus xy e to the xyz. And we want to know the partial derivative at a specific point, at the point 0, 1, 2. So I'm going to plug a 0, 1, 2 into all of these partials. And that will give us our gradient. All right, so if we plug a 0, 1, 2 into this first guy right here, that will give us a 2 times e to the 0, which is just 1, so that just gives us 2. Here, if you plug in a 2 for z, that'll give us 2, plus if you plug in a 0 for x, everything else will go away, and that'll just give us 2. And then if you plug in a 1 for y and a 0 for x, that'll just give us 1. So our overall gradient is 2, 2, 1. So this would represent the direction of the maximum rate of change. And if we want to know what the maximum rate of change actually is, we just compute the length of that. So that would be the square root of 2 squared, which is 4, 2 squared, which is 4, 1 squared, which is 1. So that would be root 9, which is 3. So this represents the maximum rate of change. All right, so we've answered that question. What is the maximum rate of change and the direction of the maximum rate of change? And then part B says, find the rate of change of this function at the point P in the direction towards the point Q. Okay, so in the last problem that we did, they gave us a vector that we were going in. They said, in the direction of this vector. So that was easy to compute a unit vector. We just divided by its length. This has a slight little curveball thrown in. They're not presenting us with a vector. What they are presenting us with is a starting point and going towards another point, so we have to compute the vector ourselves. Okay, we'll do that in 1 second, but remember, if we're finding the rate of change in a specific direction, that means we are finding a directional derivative. So again, we need 3 things. We need the gradient, which we've already computed up above as 2, 2, 1. We need the unit vector, and that's what we're going to do now. So to compute this unit vector, we are going to find PQ, because that's the direction that we're going in. We're going from P to Q. So as a reminder, point P was given in the beginning of the problem as 0, 1, 2. So PQ is going to be all the points of Q minus P. So negative 2 minus 0 is negative 2. Negative 1 minus 1 is negative 2. 0 minus 2 is negative 2. So this is the direction we're going in, but we need to find a unit vector in that direction. So we are going to take this vector here, and we are going to divide it by its length. So 2 squared is 4, 2 squared is 4, and 4. So let's see, that's going to give us root 12. And root 12 is 4 times 3, so that would be 2 root 3. So we're taking all these negative 2's and dividing them by 2 root 3's. So the 2's will cancel, and we're going to end up with a unit vector of -1 over root 3, -1 over root 3, -1 over root 3. And then if we want to find our directional derivative overall, we're going to take a dot product. Right, so we are going to take the dot product of our gradient of f dotted with the unit vector in the direction that we're going. So we're going to do 2, 2, 1, dotted with -1 over root 3, -1 over root 3, -1 over root 3. And when we compute that dot product, that's going to give us -2 over root 3, -2 over root 3, so that's -4 over root 3, -5 over root 3 overall. Nope. -5 over root 3. All right, so there's this one kind of side topic thrown on into this section, which is about finding tangent planes and normal lines to level surfaces. So if you recall earlier in chapter 14, we found equations of tangent planes before. But when we were finding equations of tangent planes before, we were finding equations of tangent planes to surfaces that were defined explicitly. In other words, it was z equals some function of x and y, or f of xy equals some function of x and y. Those were explicitly defined function because your z was not jumbled in together with your x and your y. Now what we're doing is we're taking a look at finding a tangent plane to a level curve. In other words, you have some x's and y's jumbled together equal to a number at a certain point. And if you remember, in general, to find the equation of a plane, you always needed two things. What two things do you need to find the equation of a plane? To find the equation of a plane, you need a point on that plane, and you need the normal vector of that plane. What we're saying now is if we are specifically finding the equation of a tangent plane to a level surface, the normal vector of that plane is going to be equal to the gradient of that function. Okay, this will make more sense when we do an example. If you're a formula person, you can just memorize this formula and that'll get you where you need to go. Okay. This will also tie into finding the equation of a normal line to a level surface. Let's do an example and make some sense out of it. All right, so this first example here says, here we have some surface described by this function here. Find an equation for the tangent plane to this surface at the point 1, 1, 0. Okay, so what we have here is a level surface. Notice we cannot treat this the same way we did when we found tangent planes a while ago because you cannot write this as z equals. You can try all day, you will never be able to solve for z explicitly as a function of x and y. So what we need to do here is we need to treat it as a tangent plane to a level surface. So the first thing I'm going to do is I'm going to call this right here all the x's and y's and z's that are jumbled together on one side where we have a number on the other. That is my capital F, my f of x, y, z. So the part that's not equal to the number. Okay, so if we want the equation of a tangent plane, we need a point on the plane, which is given as 1, 1, 0. And we need the normal vector of the plane. And in this particular case, the normal vector of our plane happens to be the gradient of this capital F. So if we want to take the gradient of that capital F, let's go ahead and do that. All right, so I'll do this down here. The partial derivative with respect to x is going to be 2xy plus z. The partial derivative with respect to y is going to be x squared plus z e to the z. And the partial derivative with respect to z is going to be x plus, here we're going to need to use a product rule because we have something with a z times something with a z. So it'll be first left alone, yz left alone, times the derivative of e to the z, which is e to the z, plus e to the z left alone, times the derivative of yz with respect to z, which is just y. And what we want to do is we want to evaluate each of these at the point 1, 1, 0. So at 1, 1, 0, that's going to give us 2 plus 0, so just 2. This will give us 1 plus 0, which is just 1. And this will give us 1 plus 0 plus 1, which would give us 2. So our gradient is 2, 1, 2. So now we have a point, we have a normal vector, so we can find the equation of that tangent plane. So the equation of the tangent plane so anytime you want to find the equation of a plane, we're going to use your normal vector times x minus the x value of the point. So the y value of your normal vector times y minus the y value of our point, plus z component of our normal vector times z minus the z component of our point, and set it equal to 0. Okay, so this is just the equation of the plane. If you didn't know that from chapter 12, then you can also just look up at the top of the page, and that's exactly what I'm using right here, where those are the x, y, and z values of our gradient, and this is x minus the x value of my point, y minus the y value of the point, z minus the z value of the point. All right, so continuing with the simplification there, that is going to give us 2x minus 2 plus y minus 1 plus 2z equals 0. So 2x plus y plus 2z equals 3. All right, that's the answer to part A. Part B says, find the parametric equation for the normal line to the level surface at the point 1, 1, 0. So again, I told you I'm going to be drawing a lot of domes. Let's say you have some surface, and what we just did is we found the equation of the tangent plane. So forgive my horrible 3D drawing here, but if this is some tangent plane, and we found the normal vector to the tangent plane by computing our gradient, then if we want to find the equation of the normal line to this surface, then the gradient of our function, the normal vector of our tangent plane, is acting as the direction vector of our normal line. Okay, so to kind of break that down, flashback to chapter 12, anytime you want to find an equation of a line, what two things do you need? You need a point on the line, and you need the direction vector of the line. And what we're saying here is that the gradient of f at that point is the direction vector of our normal line. All right, so our point is 1, 1, 0. Our direction vector, or our gradient, was 2, 1, 2. They're asking for the line in a parametric form, so I'm going to write this as x equals 1 plus 2t, y equals 1 plus t, and z equals 0 plus 2t, and that would be the equation of our normal line. Okay, so the big takeaway here is if they give you a level surface, the equation of the tangent plane or the equation of the normal line can be found by using the gradient as your normal vector if you're talking about a plane, or direction vector if you're talking about a normal line. One other quick thing that I just wanted to touch on, I wanted to mention because, quite frankly, I forgot, is a lot of people sometimes get confused when I take this as my f. They're like, whoa, whoa, whoa. How can you just ignore that 1? Isn't that part of the function? Isn't that important? The answer is yes, it is important. However, we are intrinsically including that equals 1 in there, because if we're looking at it at the point 1, 1, 0, it's going to end up equaling 1 there. So we've kind of inherently, without really realizing it, included that 1 in there. So it's okay to just kind of ignore it. The other thing you can think about is you can think about subtracting it over to the other side and setting it equal to 0, and then it just drops out when you take the derivative anyway. So don't worry about just ignoring that 1. That's a fair move. You're allowed to do that. All right, so that wraps up this section.